Okay, let's get started. Again, I'm Eric Brynjolfsson, and this is the Digital Economy Lab Lunch Seminar. Today we have Joel Becker joining us. He is a member of the technical staff at METR and also founder and CEO of Quali. Before joining METR, he did economic research at both at NYU, Harvard, and Oxford University. So we welcome and encourage questions. If you have like a clarifying question during the seminar, feel free to ask that. If you're in the Zoom audience, you can use the Q&A function. You're going to be able to leave a little time at the end for more general questions.
Yeah, sure.
Yeah, that would be great.
Ask questions throughout.
Yeah, and as well as throughout. So if you're here at Stanford, just raise your hand. We'll bring you a microphone over. And with that, Joel, welcome to Stanford, and tell us about reconciling the impressive AI benchmark performance with limited developer productivity impacts.
It's mouthing. Thank you very much, Eric. Thank you everyone for having me. Here's an outline of what I'll talk about today. Maybe a starting apology that the title's a bit overpromising with limited developer productivity impacts. I think with recent work, also with anecdotes that many of you will be familiar with, probably developer productivity impacts look pretty impressive today. Still, I think there are instructive things that we can say. Secondly, I'm going to get through a lot. I apologize for demanding so much of your attention. We're going to go through this time horizon work, the original paper, but also sort of broader work stream, some of the things that have been coming out of it, and then the same for developer productivity work, in particular this RCT that I worked on as part of METR research. And then we're going to suggest there's some gap between these things. I think many ways you can phrase this. I'm going to frame it as a test between as a difference between what we're measuring in test-like conditions versus deployment-like conditions. But many other framings are possible. And then I'll leave you with some open problems that perhaps you guys and certainly myself might be interested in working on, and some sort of bigger picture implications. Okay, a little about METR. We're an independent research nonprofit. The first two letters stand for model evaluation. That is, we seek to measure AI capabilities and propensities. And then the second two letters, threat research. We seek to connect those capabilities and propensities back to threat models of interest to understand the degree to which, or whether timing for whether AIs might pose catastrophic risks to society. Maybe a little background in how some of this sort of strictly capabilities-like evidence fits into our bigger picture. We have this larger set of evaluation results for GPT-5 that doesn't just look like the model cards associated with models that some of you might have seen that METR has had work included in, but rather is this kind of structured case laying out, but why is it that we think GPT-5 does not pose catastrophic risks to society? It kind of seems obvious, but at the same time, GPT-5 is extraordinarily capable, I think. More recent models more capable than that, and it's worth asking why we think this. In the end, we rule it out on the basis of capabilities. That is, even if GPT-5, even if GPT-5 sort of wanted to pose catastrophic risks, in some sense, we think it doesn't have the capabilities to do so, and that's why we're confident today that it's not posing these kinds of risks. That is to say, some of the work that I'm showing you today is trying to kind of upper bound capabilities in some sense from our perspective. Okay, first paper. This is the time horizon work associated with this chart that many of you might have seen on Twitter. Stepping back a little bit to how do we measure AI capabilities historically? Well, lots of people are familiar with benchmarks. These benchmarks have some notion of a capabilities floor, that is random performance or 0%, something like this. There's some intermediate range where we're getting signal. Then there's the ceiling of the benchmark, or some notion of human performance. Maybe past that we get superhuman performance. But how exactly to interpret this? For SWE-bench, for example, if I have a score of 40% versus a score of 60%, what does that really mean? If I beat some notion of the human baseline, am I superhuman on the relevant capabilities in some sense? It's kind of unclear. The innovation of the time horizon work is going to be to connect human task duration to some notion of AI capabilities. That is, we're first going to gather human baseline data on the same set of tasks that we're going to give AIs, and under as close to the same conditions as possible. That is, these humans, they have access to maybe a couple of custom commands that we set up for them. They have access to a terminal. Maybe they have access to some GPU resources. Exactly the same things that we're going to be giving the AIs. In particular, we're going to be measuring, of course, whether they're successful on the task, but maybe more importantly for our purposes, how long these human baseliners are going to take to complete the tasks. We're going to have AIs try to complete those tasks under, again, as close to identical conditions as possible and learn about their success rates on those tasks. And then we're going to convert this duration, this sort of difficulty of tasks as measured by the time it takes to have humans, low context humans with relevant expertise complete those tasks into an estimate of autonomous capabilities. Here's some of the plumbing. So for a single model, this is Claude 3.7 Sonnet. It was the most recent model that had come out at the time this work originally came out. We see on the y-axis we have simply the chance for a given bucket or for a given length of task the AI succeeds at this type of task. At the low end, these 1 second to 15 second tasks. These are things like here's a list of 4 possible files. One of them is called passwords.txt. Which file is most likely to include the passwords? That's as simple as that. Yeah.
Can you say a little bit about how you choose the tasks? Like, if the task was lift a box, I don't think Sonnet would do all that well. But should you pre-select things that you think Sonnet's already going to be able to do? And how should we interpret that?
Yeah. So the aspiration is to pick tasks that we think are especially relevant to AI R&D, because this is an area that METR is most interested in, to software engineering, cybersecurity, machine learning, that are as close to unselected as possible in some sense. Not exactly sure how to operationalize that, including not selected for whether the AIs are going to be performant or not performant at these tasks ahead of time. I think there are probably many ways in which we're failing at that. So, one example is we require these tasks to be fair in the sense that a low context but someone with relevant expertise, human baseliner, could in principle complete the task. And not all work is like that, right? Like there's some types of work that only makes sense to do if you have a bunch of context built up ahead of time. Another example is many of these tasks are algorithmically or automatically scored instead of manually scored, or other possibilities there, and not all work sort of neatly fits into that frame. We're going to talk about this later. I think you should think of these tasks as selected. The aspiration is for them to not be selected, other than being pertinent to this task distribution that we're most interested in.
Say there that so these are tasks to help with AI research. Is that the universe?
Yep.
You should be thinking of?
Maybe I'll also say sort of mostly text-based or tasks that are not multimodal. That's
so that wouldn't include like assembling a microprocessor or a GPU.
That's correct. I mean, in principle, we could, but
that's part of AI research.
Sure. Yeah. This is sort of largely text-based tasks that can fit into that algorithmic scoring framework that are relevant to machine learning R&D. Okay. Then at the very long end, we have these like open-ended, sort of maybe highly creative research challenges. These are things like here's a language model. It's corrupted in some way. I'm not telling you the way in which it's corrupted. Try and identify what's wrong here and get the model back to maximum performance. And then we have intermediate tasks that I maybe won't describe for interest of time. Empirically, there's nothing necessary about this, but empirically we see this sort of log sigmoidal-like pattern to these histograms of success by duration of task, that it takes these low context but high expertise human baseliners. And so we fit a logistic curve, and then we're going to call the time horizon of a given model the point on the x-axis at which we would predict 50% success probability. Lots of ways in which you can challenge that 50% success probability. Maybe I'll leave that for a little bit later, but this is the basic thing that we're going to do. And of course, we're going to repeat that for a bunch of models. I just showed you the most recent model at the time that the work came out. Here are another couple of models that were in the original work. You see they roughly have this kind of log sigmoidal-like shape to the histograms. Okay, and then you take these points on the x-axis where we predict 50% chance of models succeeding on a task of that duration, and plot them over calendar time. And you see something that looks, a little bit like an exponential. And in fact, plotted with log scaled y-axis, it looks remarkably steady in its exponential pattern. Yep. Oh, sorry.
In the log sigmoidal plots, to what extent do you expect humans to have a pattern that looks like this? And is this surprising that you get this shape?
Great question. I expect humans to have a significantly, I expect them to have a much wider, a much sort of shallower, less steep log sigmoidal pattern maybe, and for the floor to be quite a bit higher. There's a whole series of interesting questions that follow from that. Maybe also it's unreasonable to think that the floor is anything less than 100% because maybe humans can try for infinite time or something. We end up with this remarkably steady empirical pattern. And since then, the results that you see on the screen behind me aren't exactly comparable. It's a large set of tasks than from the original work. But broadly, we've seen this exponential continue. If anything, in the recent past, it looks like it's accelerating or rising more quickly. And maybe another thing to say about this, you'll notice that for Claude Opus 4.6, you can't see the top of the confidence interval. I think it's actually going up to 98 hours, if I remember correctly. We don't have tasks, as I understand it, that are longer than 32 hours or something. That's not something we want to hide behind. I think it just is the case that we have real challenges finding tasks that AIs are really not performant at today, and that's causing us to have enormous uncertainty about capabilities at the current margin.
I'm not sure I exactly understand the human comparison. So is it the idea that these are tasks that humans can do with 100% confidence or success in a certain number of hours, or 90-something% or something? Like I'm just trying to imagine if someone gave me this very long, complicated arithmetic problem. I could kind of make a first pass, and maybe I'd make an error somewhere. Maybe if I went through and checked it, not using a calculator, I would, have a higher probability of not making any errors. How should I think about what the hours are?
Yeah. So this is so one thing to say is this is conditional on successes. Which in some ways I think is a controversial choice. I think we have this somewhat opinionated view that failures tend to result from a mismatch between baseliner expertise and the required expertise of the tasks, which is related to why we filter on successes. But yeah, that's what we do. So you should be thinking about this as the average time for a particular task, because we're often collecting multiple attempts per task that it took these humans to complete successfully. And some of them, some of the attempts might not have been successful.
So you give someone a task, a set of humans a task, and then you give 100 humans a task. 70 of them completed successfully. You take the average time it took them to complete it successfully.
Yeah. And of course there's room in there for criticism, but that's the procedure. Yeah.
So follow up to that. For example, you said implementing complex protocol for multiple RFCs.
Sorry, could you possibly repeat that?
Yeah. So following up on what he said, one of the tasks says implement complex protocol for multiple RFCs. Are those known RFCs? For example, implement FTP, or is something that is brand new that no human has ever heard about? And second follow-up question, if it is a brand new one, how do you know that the implementation of the AI is secure and it meets all the requirements of mature RFC?
Great question. I do not know the answer. Many of these tasks, past the hour mark, maybe let's say, are beyond my personal capabilities. And so I've slightly lost track personally of what's in the task distribution. So my colleagues have more expertise. Okay, I'm going to skip through some internal, external validity stuff for time reasons, although if people have questions about that, I'm happy to answer.
Sorry, one more thing to say about those S curves, which are really cool.
Yep.
I think I heard, so you had it for the 50th percentile.
Yep.
If we were to say 90% likely to get it correctly, would it sort of be consistently the same shape, just shifted to the right or to the left, to the right?
So we do show this for 80%. One tricky thing is that, given that we're using these logistic fits, 80%, the parameterization for 80% is not independent of the parameterization for 50%. So I'm not sure how strong evidence this is. Also, as we're getting to, if we were thinking about 99% or something, we wouldn't have enough tasks to estimate that reliably, especially when you incorporate the possibility of label noise or sort of successes where actually we see failures or the reverse. That said, colloquially, informally, my expectation is that we'd see approximately the same kind of trend. That is similar slope, but very different level in economics jargon. Cool. Stepping back a little bit, I think you should think of time horizon evidence as having a similar profile of pros, but especially cons, to other benchmark style evidence. These are still sort of self-contained, not very messy tasks. These are still sort of selected in some of the ways that we gestured at earlier. But what are some things that we can get out of the benchmark style evidence? I think one thing, as my non-answer here points out, is that AIs can succeed at what for humans would be extremely challenging tasks. Maybe they're selected in some way, but I think it's hard to refute that. Another is that maybe this is more opinionated. Progress is rapid, but also it's sort of surprisingly continuous over time, where it feels remarkable to me both at the time that we saw this steady exponential, and also that something like that steady exponential, or in fact something faster than it, has proceeded somewhat continuously. There's this METR slide deck from before I was there, around 2023 or so, where we're pointing at some of our sort of aspirations of our research program. There's this illustrative graph. It has, I think on the y-axis, some notion of dangerous capabilities. And on the x-axis, it has time or compute or resources or something. And what you see is this sort of enormous cloud of points that broadly has an up and to the right shape, but is very, very noisy. I think we did not expect something so empirically regular, something so continuous, but that is what we find. Sorry, did you have a question? No, cool. Great. All right, that said, some limitations, very, very non-exhaustive set of limitations from this work. One thing, as mentioned, the baseliners are low context. If these are cybersecurity tasks, they have expertise relevant to cybersecurity, but not intimate familiarity with exactly this task in particular. It's not necessarily something that they've seen pop up in their work previously. Maybe you should be thinking about the experiences that they're coming in with as kind of analogous to people on their first month or first day on the job. Yeah.
For the microphone. You've trained us well. I wanted to ask, these tasks, are they secret or it's publicly available? And how are you worried about the modelers training to them and gamifying what you're doing?
So there's some variation here. So the RE bench tasks, these 8-hour sort of very challenging ML problems are fully public. You can find them. Some of the quote unquote HCAST tasks, these are tasks in the middle of that kind of 1 minute to 30 hours distribution. So some of those have been released publicly. For the most part, they're private. The short tasks are all fully private. Yeah, I think there are some empirical tests you can do to suss out, degree of contamination or memorization. It is a constant worry. I would say a related worry that I feel more strongly is that the kinds of factors that lead it to be easier for us to measure performance on a particular type of task, correlated with the kinds of factors that make it easier for model developers to train on those types of tasks. These like neatly contained environments from the perspective of both groups, a sort of lower cost to get an equivalently complex problem. And so in some sense, we're measuring success or measuring performance on exactly the tasks. Not precisely the tasks, but something close to the task distribution that you might expect a priori model developers to be training on. That is a live concern that you should have front of mind. Another limitation here, maybe there's some sense that the benchmarks are low ceiling. Once you get 100%, presumably there's more performance you can go on that style of task. There's some notion of superhuman range. You can imagine for optimization style problems, you can get to the points that we said a human baseliner would take 8 hours to get to, but maybe there's further you can optimize on the particular challenge. That is we're imposing some sort of low ceiling here. And some notion of messiness, or these tasks being highly filtered in some of the ways that I've spoken about. Some of these challenges are somewhat more sort of open-ended, or requires more management of external resources, or this sort of thing. They're kind of larger, more open-ended environments. There's some variation within our task suite, but for the most part, these are on the more sort of closed, not messy ends, even if they're very technically complex. Yeah, question?
I'm thinking about feed forward and feedback in tasks, and how fine-grained feedback's required, and that's always an issue. And of course, then the question is collaborative. That gets even more fancy and confusing about feedback.
Yeah. One thing to say here is that these task attempts are totally autonomous. There is none of this feedback. Presumably we'd expect performance to be greater if people were getting some feedback from humans. In some sense, the humans are operating under similar conditions, but I still think it's very relevant. Maybe one other thing to say there is one common misconception about time horizon is that this is the length of tasks that the AIs are productively working for. And as I referenced back to several times, this is the sort of difficulty of tasks that AIs can complete, as measured by how long it took humans to complete them. The level and maybe even the trend of these numbers would be sensitive to exactly what you're pointing out, or possibly would be sensitive.
The time is how long it takes for the human to do it, but AIs also do better when they work longer, as they do more inference. So what should we be thinking about in terms of like letting the model run for a long time versus, I guess earlier it was just like, okay, it gives you the answer. Now it can go off and think for quite a while and use a lot of tokens. And so where do you, and it gets different or hopefully better answers when it thinks longer.
Yeah, so the analogy that I think will sort of convey most understanding in short time or something is you should think about these AIs as because we're not trying to measure this length of time that they're working for, you should sort of think about them as completing the work in 5 minutes. But also you should imagine that we're attempting to measure the ceiling of their capability. That is, in the background, we're letting them work for as long as seems reasonable to them until they get sort of maximum performance, until performance is fully plateaued off. And that's the point at which we're measuring success. So for some of these harder tasks, we're often having sort of 8 million token runs per attempt on the task.
So increasingly, they're
a maximum of that. Sorry,
they're thinking a longer time. And yeah, so I guess at some point you'll want to have another dimension, which is how long you let them. I mean, at some point it gets really expensive to have them run for millions of.
So I think you'll. I don't want to promise, but my understanding is that you'll see in some upcoming, not released meter work, runs of up to sort of several billion tokens. Those are getting into the $1,000 range per run. All right, these were some of the limitations. The baseliners are low context. Perhaps we think capabilities were less impressive if we were measuring against sort of more expert in the sense of more familiar baseliners who presumably would complete these tasks in less time. the ceiling is low and the tasks are somewhat selected, or in particular, they're not very messy, quote unquote. Maybe field experiments is the answer, or at least this is something that we hypothesized around early last year when we set off on this work. Here, we're going to take very high context developers, as you're about to see, both in the sense of highly expert and in the sense of intimately familiar with their particular project. Maybe you think that speedup gives you some notion of the degree to which you're sped up on some tasks, gives you signal through a greater capabilities range. That is, it's not merely that you hit this ceiling of 1 on the optimization problem, but even more performant AIs can help you get sped up even to an even greater degree. And then lastly, we're going to take people's real tasks, in this case, real issues that they've posted to GitHub. These are non-synthetic. This is real deployment scenario. This is no longer fully autonomous agent capabilities. This is humans working with AIs inside of Cursor early last year. Okay, here's in a little bit more detail what we're going to do. We're going to take 16 experienced, as I'll describe, open source developers on some of the largest, most mature projects in the world. They're going to complete, on average, 16 tasks from their real issues on these repositories. There's some selection in that we ask them, if possible, to take tasks, I think, that are more than 4 hours or 8 hours, and chop them up into smaller tasks for power reasons. Although that's not always the case, we do capture some longer tasks. For the most part, I think you should be thinking of this as just their unselected real issues. We're going to randomly assign their tasks to simply AI allowed or AI disallowed. AI allowed means everything that you think it means. In the context of this experiment, it mostly means, because we paid for Cursor access, using Cursor, the agentic programming tool. And AI disallowed means software engineering in 2019. It means sort of no AI-powered tab autocomplete. It means it can mean Google, which nowadays does have some AI power, but it means no LLMs via the web UI, no Cursor, etc., etc. And then we're going to record the time it takes them to complete each task and ask the degree to which people are saved time when they have access to AIs. Okay, here's some color on some of the repositories that are included, some of the repositories that the developers are working on that are included as part of our study. For those of you familiar with open source development, you'll see here the Haskell compiler, GHC. You'll see Hypothesis, standardlib.js, scikit-learn, Hugging Face transformers. These are very long-lived. I think they've been around for 10 years on average, maybe 1 million+ lines of code. The developers who are working on these repositories are on average the 3rd top contributor to the repository. They've been working on the repository for an average of, I think, 5 years, out of something like mid-hundreds number of contributors total. Some of you might have seen this chart, so it might have been spoiled for some of you. The punchline goes as follows: we ask experts ahead of time, economics experts, machine learning experts, the degree to which people are going to be saved time when they have access to AI. They tell us that people will spend 40% less time when they have access to AI. We ask the developers ahead of time on a per issue basis how much quicker they're going to complete the tasks, and they say it'll take 24% less time when they have access to AI. We ask those same developers, after the study has been completed and they've recorded all their times, that they have access to their time still when they're making this retrodiction, how much they were sped up in the past on the issues that they completed as part of this study. And they say that AI made them complete tasks in 20% less time. And we find actually that they take 20% longer to complete tasks when they're allowed to use AI versus not. There's a bunch of implicit caveats in this title. These should be front of mind. This is not something that we're shying away from in any way. These are extremely experienced, extremely familiar with the particular challenges. Developers working on these extraordinarily complex projects in early 2025 with the AI tools of that time. I remember early on we were collecting the data. The point estimate actually was always negative as the data was coming in, and so we assumed, perhaps what some of you are assuming now, basically that we messed up, that maybe we had some sort of sign flip going on somewhere in the data, and so we spent a long time trying to categorize, the possible reasons why we'd we'd be seeing this negative result, all the way from coding bugs to the factors that we eventually end up with. Really trying to exhaustively probe the data for explanations. The data is small; it's 250 issues, and so I think that actually there's not much that we can say about many of these explanations. It's not the case that we have convincing evidence against them in some cases, although in other cases I think we do have somewhat convincing evidence. It's more the case that we can't say, but we're trying to point to some of these factors regardless. Some of the factors that we think are contributing to slowdown. So you might think from this chart I showed you before, where the developers are pretty optimistic about how much AI has sped them up, too optimistic, in fact, that they're going into their issues with these expectations that AI is going to speed them up a bunch. Actually, that's not the case. They end up overusing AI, and that's part of what's causing them to go below the 0 point. That's a great question. This is mostly Python. I'm not going to be able to give you the full breakdown on the spot. I think there's some JavaScript. I think there's some Rust and C. Sorry, I don't have a clearer answer. Yeah.
So when I'm collaborating with somebody else that I'm not used to, the communication time and trying to understand their solutions will slow me down. Is that part of the issue here?
Yeah, this is. Actually, I think we don't really have that here, but I will discuss that later. I think that's totally the case. Or another analogy that might make sense is note taking, where there are a lot of these AI note taker apps, and they fulfill sort of part of the role that note taking is supposed to take. That is like having a recording of your meeting notes, but they're not like helping you form memories, or they're not sort of helping you think in live about the meeting. If you use an AI note taker app and you're wanting to take away some of those benefits, maybe you won't get it, because it's important to understand the creation of the solution, what the possible solution space was ahead of time, why you chose this direction rather than another direction as part of completing some next task. Yeah, I think that's a real thing going on here. Cool. Some more factors. I've already mentioned that these developers are very highly familiar with their work and that these repositories are large and complex. Another thing related to what Eric was pointing out, we were talking about 50% reliability previously. You should think of 50% reliability as being somewhere between, but a little bit closer to 50% of tasks of this length it can complete 100% of the time, and 50% it can complete 0% of the time, rather than for all of these tasks of some length, maybe an hour, it completes all of them 50% of the time. So it's a little more complicated than it might seem at first blush. But that's one possibility. Maybe you need 99% reliability at the 1 hour time horizon to get speed up on tasks of an hour, something like that. Yep.
They're very familiar with the repositories. Had they been working with Cursor? It was mostly Cursor, right? Had they been working? Has some of them working with it before? Or was it new to all of them, or what was their level of familiarity with the tool?
Yeah, Cursor was new to 75% of them. 25% of the developers had used Cursor ahead of time. Almost all of them had used some sort of AI tools. I think 15 out of 16, if memory serves, were using at least web UI based LLMs, and then for intermediate tools like Cursor and Copilot, somewhere in the middle, north of 50%. And I think maybe there's an implicit question in there about whether this is driving results.
Yeah, whether like the people who hadn't used it before, it took a while to get up to speed, made some mistakes, and and people who, I would imagine, people who used it more were could hit the ground running a little faster.
Yeah, I controversially say that's not my primary understanding of what's going on here. We present some quantitative evidence in the paper relating to this that I don't really buy, basically. When you exclude people's first issue on which they're allowed to use AI, exclude the second issue, exclude the third issue, so on. That is, when you try and get at these learning effects where they become more capable at using AI as time goes on, we don't observe anything. I think that evidence is quite underpowered. This is more controversial, but roughly my read is that when you segment to developers who had more or less AI experience ahead of time, I'd say you basically don't see much, although that comparison as well is underpowered. The thing that really convinces me is, again, as part of thinking that this result was bananas and trying to come up with all possible explanations, we watched hours and hours and hours and hours of these developers working with AI, and I would say they were pretty in distribution for METR users. Some people are making mistakes, or uses of AI that I would consider a mistake, and in many of those cases, we correct their usage of AI. Some of the developers are using more advanced workflows than we at METR were working with at the time. And further, I guess that METR is pretty in distribution for what's going on at AI labs in terms of complexity of AI usage. Yeah, hard to communicate that to you, but that's the thing that I find convincing.
I'm curious about the control group, because if you're literally talking about the main contributors to the Haskell compiler, I would expect that they're like muscle memory on Emacs, God mode, and it could literally be just forcing these people to use a GUI-based thing drove a lot of the results, but that doesn't seem to be on your explanations. How do you rule that out?
Yeah, I think that's not framed very well in terms of these factors. Yeah, that seems like a live concern to me. These are extremely skilled developers, and I think if we were working with less experienced developers, then possibly on these same problems we would see significantly positive speed up even at the time.
Well, or here just to say like an Emacs that integrates AI would be so much better that here actually cursor the interface is the problem, that it might be slowing them down.
Yeah. That seems pretty plausible to me. Another related concern is that maybe Cursor's elicitation of capabilities is not what you might want it to be. Maybe they could be spending more tokens at the time, something like that. And so, maybe with the tools being changed in that way, we would have seen greater performance. That seems very alive. Maybe one thing to say on the control group: we're randomizing at the issue level, so the control group is the same developers, but for the issues where they're assigned to no AI.
Yeah, are you measuring wall clock time, or you're measuring the effort time? Because let's say I'm a developer and maybe a task would take me 4 hours of my effort time. But what I do is at 6 o'clock in the evening, I kick off all the AI jobs. I'm off the clock, and I come back the next morning, and now I spend maybe only a fraction of my time doing all the edits and all of these kinds of things that you're talking about here. Are you counting the time that elapsed in between those two moments, or no? You're saying, hey, he checked out at 6 o'clock, he started again at 9 o'clock. We're not counting.
This is imperfect, but basically you should think of us as measuring effort time. So we do observe. We have some labeled video recordings. You can see this more in the paper, where we show that for some of the time it appears like people are not on task. It seems not quantitatively important enough to explain the result. Yeah, but for the most part, we're estimating effort time. Yep.
In a way, it's an observation. This, I believe, shouldn't be too surprising, because I would assume that the issues that you tested these people on are open issues that are probably not containing the training set. So if you are a super guru on whatever, so statistical pattern matching is not human intelligence. There's whole debate about whether understanding can be codified in an algorithm, but I wouldn't be surprised that if you pick, for example, the top expert at Stanford on a particular issue, and you give that to an AI, and you force the top expert at Stanford, like mathematician or something, he's going to be a slowdown because he just have that spark of creativity that AIs don't have. So I don't know.
Yeah, one angle on that is I think that's a very real part of the explanation. On whether that makes it not surprising, experts find it surprising. I would, and my expectations, I'd say, we're not so far away from the experts personally. It might be worth saying that when we set about this work, we weren't thinking like, what's the case where the AI is the least performant or something, and let's measure that particular area. We were asking, from a perspective of very practical constraints, where can we most easily get data? And the answer was for these very experienced open source developers. But maybe you had better expectations than me. Cool. Here are some factors that we think have an unclear effect on slowdown. I won't spend too much time on this. One of the things here is this below average use of AI tools that we referenced with Eric earlier. There's also some factors that I won't go through now that you can find in the paper where we think we've ruled out that those factors contribute to slowdown. Okay, Here are some takeaways. The first one's kind of ironic. It's that surveys are unreliable. That is, we ask people the degree to which they're sped up. We ask experts the degree to which other people might be sped up, and clearly people are giving answers that ex post look incorrect. I am now working on surveys of the degree to which people are sped up. There's more to say there. I think there is a lot of noise in these kinds of estimates. One reason I think this is an important takeaway is that, that method of just asking machine learning researchers, to what degree are you being sped up? That's an alternative method that's been proposed for measuring AI capabilities. I think in the recent Opus 4.5 model card, one piece of evidence that Anthropic rely on is this survey of 16 developers, where they ask them the degree to which they're being sped up. And I think we should have real somewhat severe questions about the quality of that evidence. Yep.
On the surveys, did you at least find that the people who thought they were sped up more had more sped up, or was it like just noise? Like, was there any within survey response signal?
So now we're super underpowered. The 16 developers. There's a strong positive correlation. For what it's worth, given how underpowered it is, between people's estimates ahead of time and their predictions. The people are very optimistic about being sped up beforehand, are very optimistic about having been sped up after the fact. And there's a somewhat of a negative correlation, a weak negative correlation between that and their actual speed up. That said, within developer, the issues for which people expect to see more speed up are, on average, get something like 0%, and the issues on which people really don't expect to see speed up are slow down more. So there's, a complicated picture on the degree to which people are calibrated here. Yeah.
Hi, yeah, my name's Deepak. Pretty interesting presentation here. I guess I have a few questions, but I'll summarize them as such. So in the METR, how is the threat analysis done? And the second question I have is from a perspective of someone who is developing LLM benchmarks. What is your benchmark apparatus? How do you ensure consistency? We're talking at the hardware level, network level. And one of the things I've always questioned in these kind of studies is the ability for the agent to access fresh information from a live internet versus something like an archived version of the internet versus no internet. How much of a factor do you think that makes in your accuracy or recency here?
If you don't mind, I might leave the questions to the end. I think both of those could easily be a 10-hour-long talk. So it might take a while. Okay, the second takeaway here, many of you will be familiar with this takeaway from many other papers in AI. Benchmarks don't tell the full story. Okay, so here begins some extra work that we've that's come out since then, and some sort of pontificating or editorializing that I might do for the rest of the talk. We have continued this same study design with the same developers that were included in the previous study and new developers. And I'd say the broad takeaway is that the data isn't good enough for us to draw reliable conclusions. In particular, I think that developers who expect to be sped up very significantly are systematically dropping out of our data. So we're left with developers who expect less speed up. And on the issue level, within developers, the issues for which developers expect more speed up, they systematically do not contribute to the study. We still measure point estimates that are I was going to say positive, but negative, that they're taking less time. But actually, I think this is sort of significantly understating the degree to which people are sped up today. This is not even including the possibility of concurrency, which I think was less important at roughly March 2025, the time of the previous study. That is, you ask your AI to go about solving task 1, and then while it's working off on that, you go about completing task 2, maybe also with the AI. We're ignoring that concern here, and you'd expect that to lead to, in some sense, even greater speed up. Eric and I were talking before about the ways in which we might be able to resuscitate the study design. I'd be very interested in talking to people about that afterwards. For now, maybe I want to leave you with on this work, both that we don't have the ball here, or that the state of this study design is not great. We're going to need to lean on other means of capabilities measurement, and also it's kind of a data point in and of itself that it's difficult for METR to get developers to work without AI. Okay, here's some other recent work. Maybe I won't spend too long on this. You can imagine just looking at, in some sense, a 100% AI condition.
So it's interesting that, these folks didn't want to work without AI because they thought it was so important. But what happened when you showed people who were in the study, 16, that they actually worked slower? Did they look at that and said, oh, I guess I'm not going to use AI? Or did they say, I still want to use AI because it's more fun or something? I don't know. Or, did you talk to those people about whether they had updated whether or not they wanted to work with AI?
Yeah, better than that. We have revealed preference. We, I think, maybe accidentally continued paying for these original 16 developers' cursor usage for many months after the experiment. So we know something about their retention. And I can't remember just how high retention is, but I think it's something like 80 to 90% of these people are continuing to use cursor.
So talk through what you think is going on there, because you showed them that they're actually slower. Did they not believe that they were slower, or did they say they didn't care, or did they feel like they were better now? What's the best explanation?
I think there's not a single explanation. Part of it is that these developers aren't purely optimizing for time it takes to complete tasks. They enjoy using cursor more as a sort of workflow set of ways of going about their work than they do working without cursor. Also the AIs have become considerably more performant since the time of the study. Cool.
Did any of them say, I don't believe your numbers or something? Or
no, there are these, it would take you a long time trawling through my Twitter account. There are these 5 or so developer threads or very in-depth blog posts that many of the study participants wrote, in which they talk about how it was to participate in the study, their reactions to the results. One of these posts actually came out before the results were released, which is kind of interesting. And to my knowledge, none of them have that reaction. They will find it understandable after the fact. Cool. I'll briefly talk about this work. Imagine that we had a 100% AI allowed condition. This is in fact looking at people's work internally at METR. We see them go about, accomplishing task 1 and task 2 and task 3 purely from their software engineering work, so excluding, meetings or writing documents or other sorts of things they're doing. And then we tag, maybe by asking them, or maybe by asking an AI how long that task would have taken them without access to AI, and then we divide one by the other to get some notion of speed up. It's going to be a bit too long for the talk, but I think you should think about that estimand as, for various reasons, an upper bound on the degree to which people are being made more productive. Anyway, this is an early research direction, and this is what we find: a lot of variation across staff members, and also these kind of extraordinary ratios between the time it would have taken them without AI to complete the software engineering work and the time it in fact does.
Right, just to be clear, that x-axis, those are like multiple, like 2x,
yep.
4x.
Yep.
This isn't like percentages. Like before you were looking at like percentages. Yeah. Now you're working at, factors of up to 10 or 12. Yeah.
Yes, that's right. Of course, the task distribution is quite different. Previously, ex ante, people are, actually, it's a bit more complicated than that because I think the original tasks weren't so selected. But one thing you could think is going on is that originally the developers are selecting their tasks for the kinds of tasks that wouldn't be so painful to do without AI. Whereas these are tasks that are much more straightforward to do without AI. These are tasks as part of people's natural work.
Also, I'm just noticing that 2 different colors of dots, they're the opposite way around from before.
I think I need to skip over that for the interest of time, although I can come back to it. Cool. Here's some comments on the possible puzzle. These AIs, at least at the time, we thought they were remarkably performant. Sonnet 3.7 getting a time horizon of something like 1 hour, and yet these developers are slowed down. Naively, these 2 different results seem to be pointing in opposite directions. How do we reconcile this gap? I think one possibility is we messed something up. We try to categorize these factors and so on and so forth, but it is a small study, perhaps these developers really aren't so capable of using AIs to their maximum potential, so on and so forth. Also, on the time horizon side, the state of eval science is pretty early, and I think there are some ways we could be messing up there. Okay, but let's condition on not that, on we haven't messed something up here. Here's an opinionated perspective. I think we traditionally measure AIs under conditions that are optimized for them to be most performant, and then we deploy them under conditions optimized for humans. Here are 3 ways in which I think that's the case: super not, mutually exclusive, completely exhaustive. I think the implicit playing fields from these 2 different types of evidence are quite different from one another. The scoreboard, what counts, how measuring performance is quite different. And finally, separate from those 2 factors, there are these frictions translating raw capabilities into productivity. Here are some examples of the kind of thing I mean. So for playing field, we referenced a bunch of times that in one set of work, we have these low context humans. In another set of work, we have these very high context humans. Seems like that matters. Another is capability elicitation. So a ton of work at METR has gone into making these AIs as performant as possible on a held out set of our tasks, so that we can get closer to measuring something like an upper bound of performance on the test set of tasks. And maybe the same isn't true for Cursor or for work with AIs in the wild. Another is task distribution, that these second set of tasks, both they're systematically different in a bunch of ways, also they're not selected in the way that we've spoken about a couple of points in this talk. On task distribution, here's some work that's come out since that you might be interested in. The human baselines data, I'd say, is lower quality for this work than some previous work, so maybe take some of this with a pinch of salt, but at least to communicate a mental model that I have with you. I would say that for text-based tasks that are selected in similar ways to the ways in which we spoke about these METR tasks were selected, both the slope, the speed of time horizon trends, and also the levels are, to me, surprisingly similar. But for anything that we look at involving vision capabilities, the levels are quite a bit lower. The models are, I'm not sure exactly how much this is, but 2 orders of magnitude or something, as measured by time horizon, less performant. And you might think if these tasks are messier in some sense, to first order, it's a little bit like bringing down the level of capability that we might expect to see. Then for scoreboard, here are 2 different factors I'd like to bring out. The first is, of course, on benchmarks, we're rewarding success regardless of how long the AIs are taking to complete tasks, whereas in the uplift style work, we're coming closer to measuring the time it takes to complete tasks. Is the time for humans to complete tasks with the AIs? It's a little bit more complicated, but these are being scored implicitly in different ways. And then second, related to some recent work that I have out with Parker Whitfield and some collaborators, is this difference between SWE-bench-like or automatic algorithmic scoring and manual, or would this be merged into main-like scoring? I think I can't spend too long on this, but here's a headline graph from some work where we take solutions from various AIs from epochs data to SWE-bench, and then we have maintainers, that is, people working on these projects that are represented in SWE-bench, assess whether those PRs, whether those units of work would be merged into main or not, whether they'd accept this as production quality code, both for the original sort of gold standard human solutions, the actual solutions to these PRs, and various model solutions. It's a little more complicated than this, but broadly we find that normalized for noise in whether they would merge these gold standard human attempts, about half of the cases that SWE-bench measures as passing these algorithmic tests would be merged into main by these maintainers. That is, there are cases where code quality isn't what it should be. There are some cases in which the tests aren't capturing code that is actually failing in some way that's important, that mergeability like scoring is capturing. I think this is another thing that's going on in this difference between time horizon like algorithmic scoring work and this sort of messier productivity like work. And then something on translation friction. So we mentioned earlier this interdependence across tasks that might matter quite a bit. We also mentioned that maybe reliability needs to be very high to save time on some tasks that takes humans some length. We also mentioned challenges with concurrency and latency. That it's difficult to work on multiple tasks at the same time, or if you're waiting around a lot, if you're not working on multiple tasks at the same time, you're waiting around a bunch for the AIs to complete that smaller unit of work before you give it some next set of instructions. That also introduces some frictions. And we referenced that developers perhaps aren't optimizing for speed. They continue their Cursor subscriptions they continue using Cursor after the study, even after we showed that it's slowed them down. Here's a new frontier, the survey that I mentioned earlier. If you are interested in going to this link and filling out my survey, I would appreciate that very much. The thing that I'm trying to get at in this survey is differences between value uplift and speed up. Here's an extreme example. Let's say there's some task or some job where you're just looking at the training logs as part of some machine learning experiments. Maybe now with AI you can review 3,000 times as many training logs as you could previously, because the LLM can go over each of them very, very quickly. How much more value are you getting from this task? But for some notion of value, it's clearly not 3,000x. Maybe it's 1.2, maybe it's 3. I'm not sure, but naively it seems like speed up can greatly overstate the degree to which people are getting more value out of AI. It could go the other way if people are enabled to do types of tasks that they wouldn't be able to do that are providing them value because they're complementary to some of the other tasks that they do. Okay, here are some open problems quickly that Andy asked me to point at. One thing that I'm thinking about that I'd love for many of you to think about is these very long horizon tasks. Some things that we're doing at METR in this direction at the moment include these manually scored tasks, which just opens up a bunch of constraints that we were implicitly imposing upon ourselves from algorithmic scoring, or optimization tasks, these tasks that can go above the human ceiling, that can get even better solutions than we've seen contributed by humans in the past. Related to this is how well will current model capability spike generalize? So I think some of you might have seen the C compiler work from Nicholas Carlini at Anthropic, where he shows that with many caveats, Claude Opus 4.5, 4.6 is able to produce a functioning C compiler by running for an extremely long time, churning through an extremely large amount of tokens. There's something about this replicating very well-specified software tasks that these AIs are extremely performant on at the moment, much more so than I think for other areas of the task distribution. And there's some question in my mind about how well that generalizes to other types of tasks, as we might see capabilities on that spike explode over the next year. So some other things that I'm interested in, relationship with value, which you spoke about, estimates with telemetry and or surveys. I showed you briefly the chart from METR work that you can find on the METR Notes blog. Some alternative angles on AI capabilities. I think people haven't used transcripts as a source of information nearly enough. That is, these logs of agents taking actions seems to me like a pretty interesting observational data set. And there are all these there's all this observational evidence that people are contributing in the wild on Twitter, and I imagine that there are systematic ways in which you could study that to glean some more information about AI capabilities. And here are what I think are some big picture implications. So this is what I had on previous versions of the slides, before this updated work, showing that developers, it looks like, might be very significantly sped up for the present day. Probably when we were measuring developer productivity around March 2025, some areas of R&D were not being sped up. I'm not saying that the task distribution that we looked at, the developers we looked at, are representative of everything, far from it. But probably some areas of R&D, which at METR we care most about, weren't being sped up. I think that's, in some sense, evidence about levels and not evidence about trends. AI capabilities were proceeding very rapidly at that time, even if for some task distribution, they were starting from a low level. As we think about this report, on this GPT-5 report, and how we might rule out models being catastrophically dangerous, I think exponentially increasing model capabilities suggests that we're going to need to innovate on finding out the ways in which models are incapable, or retreat to our ability to monitor these models not committing harmful actions. Yeah, and I'd maybe leave a very opinionated view with you that, in my view, transformative AI, intelligence explosions, the whole thing, in the next small number of years would not violate any current trends in AI. It's not to say it will definitely happen, but to me, something like this is the big question of the field, maybe the big question of our time. With that, thank you very much for listening.
Thank you. Well, that was amazing. Sadly, we're out of time, but you did get a lot of questions during it, so very much appreciate that. So our next speaker on April 6th will be Subhateem Sakar from the University of Chicago. So see you then, and thanks again.
Thank you very much.